No i potem praktycznie już po tej magisterce dołączyłem do Salesforce'a na pełny etat, żeby robić research. Jeżeli chodzi o Salesforce'a, to zajmujemy się researchem w różnych dziedzinach. Mieliśmy prac związanych z właśnie przetwarzaniem języka naturalnego, ale też mamy prace związane z przetwarzaniem obrazów, computer vision, też mamy reinforcement learning dosyć sporo, zarówno reinforcement learning w zastosowaniach powiedzmy modelowanie jakieś ekonomiczne, ale też reinforcement learning w zastosowaniach takich bardziej industry, powiedzmy, jeżeli chodzi o zarządzanie data centers i tego typu projekty. I zajmuję się również nie tylko takimi, powiedzmy, projektami stricte researchowymi, które idą pod konferencje, jakieś publikacje, ale też mamy taki bardziej applied dział, który współpracuje z Salesforce'em jako firmą nad takimi produktami, takimi AI-based, powiedzmy. Tak.
Działamy,
możemy zaczynać? Super. Prezentacja będzie po angielsku, bo szczerze mówiąc nad machine learningiem nigdy nie pracowałem po polsku, więc myślę, że tak będzie po prostu łatwiej dla wszystkich. Super. So today I'm happy to present my work on text summarization. As I mentioned, I've been working on this topic for about 4.5 years, so I'm really excited to present some of my insights and my findings that I've personally done or that I've done with the team at Salesforce. So the agenda for today is that we will have a brief introduction to text summarization. We'll discuss what is summarization and what are the common approaches to summarization. We'll discuss the current research setup, so I'll talk about the models, the data sets, and the metrics. And next we'll move on to chatting about the existing challenges of text summarization, and we'll close the presentation with some future directions, so pretty much promising directions for research in summarization, and I'll also highlight some of the work that we've done in our research lab at Salesforce. So as an introduction to summarization, maybe by a show of hands, how many people have worked on summarization or have an idea about summarization? Okay. Okay, so we will go through this so everyone is kind of on the same page here. So let's start this conversation about considering text as a form of communication. So text it's pretty much ubiquitous at this point, both in private life and in kind of business settings where we communicate over emails, long documents. We also read books, and text as a form of communication is pretty good because it's robust, but also has some downsides. And those downsides are, first of all, text is kind of slow to read, especially if it's like long technical documents. They're very long and slow to read and comprehend. And also, text does not adapt to the reader's knowledge. So once something is written as a document, it will not adapt to the knowledge of the reader. So pretty much if we have, let's say, a legal document that uses very technical and kind of domain-specific language, and we have a layman who's trying to read this document, they will have a hard time because the document will not adapt. So text summarization kind of aims to address some of those downsides. And pretty much the high-level goal of text summarization is to rewrite long documents into a shorter form that's still human-readable, but it preserves the most important facts from this source document. And there are three common approaches to text summarization. So the first approach is extractive summarization, where we pretty much where the model is expected to copy important parts from the source document into the output, and we can think of this as just as a human would read the document and just take a highlighter and just highlight the important parts of the document. This specific form of summarization requires the model to first of all understand the language, and second of all to be able to quantify what are the important parts of the document, so it can extract them. So it's kind of like almost like an intersection between natural language understanding and information extraction. A second common approach to text summarization is abstractive summarization, where the model paraphrases the salient parts of the document to create novel sentences and have like more of a coherent and fluent summary as an output. And this is done usually in an end-to-end fashion. And this is, I guess, most similar how humans would summarize a document. So we read something and then we just kind of build a structure of the document in our head and then just write down what we think is important. And on top of the language understanding and information extraction capabilities, the model also has to have some generative components so it can actually generate the summary. And the third common approach to summarization is a hybrid approach where we first explicitly extract the important information from the source document, and next we apply that to an abstractive model or some other paraphrasing model to kind of generate this coherent output. So some examples, if we have a news article that's talking about Microsoft trying to acquire Activision Blizzard, we can imagine that maybe let's try to shift this a bit. So we can imagine having extractive summary can be thought of as bullet points, for example, whereas an abstractive summary would be this kind of nice and coherent output. Even though they do cover the same topics, we can see that definitely the abstractive summary is more readable. So it is the more promising of the two directions, or one of the three. And when it comes to the approaches and the models used for text summarization, they pretty much kind of roughly follow the architectural trends in NLP as a broader field. So text summarization is pretty much a sequence transduction problem. So we have one sequence as an input and another sequence as an output. So using encoder-decoder models for this problem was kind of like a natural first approach when the field moved to using neural models. And at that time, around 2014, obviously the underlying architecture for those encoder-decoder models were RNN-based. So we were using LSTMs and GRU models. And they were performing quite well, but one of the downsides of those models is that at that point they were working with a very usually small-sized fixed vocabulary. So for example, for summarization, where we have a lot of documents that are, for example, news articles and contain a lot of entities or entity names, if those entities were not known to the model kind of during training, so they were not in the vocabulary, the model would just kind of output out of vocabulary tokens, which would in turn lower the quality of the summary. So the next step going from the encoder-decoder models was to augment them with attention mechanisms and pointers. And here the promise was that the model would be able to better kind of understand the document, but also the pointing mechanisms would allow the model to kind of generate some of the content, but it will also allow it to copy directly from the source some tokens, which was pretty much a promise to solve this kind of like out of vocabulary problem. Then around 2017, there was quite some interest in kind of multi-objective training, where we wanted to train models using RL-based training with sometimes non-differentiable rewards. And here the goal was to usually either improve the abstractiveness of the summary or in somehow the relevance of the summary. And then late in 2017, at NeurIPS, the transformer models was introduced with the attention is all you need paper, and that was kind of like a big shift in the NLP landscape. One of the problems that it solved is that the transformers started working on this kind of like word piece level, so subword level, so that handled a lot of the out of vocabulary problems. But one of the downsides of transformers, on the other hand, was that they had this kind of n-squared memory complexity, which in case of longer sequences, that was problematic. So after transformers, we had the whole wave of pre-trained models, and of course BERT was one kind of representation of that. And at first, those models were limited to only NLU, but later they were extended to also have the generative component, so we could start using them for summarization. But here still those models were trained usually to handle inputs up to 512 tokens, which in case of summarization, I guess the biggest benefits of the field is when we actually can handle very long documents, so beyond, let's say, the 500 tokens. So the attention of the field kind of shifted to working on the more kind of the efficient memory efficient transformers, such as longformer or reformer. And that was around 2020. And of course, we have the foundation models, which became popular around 2021, and that was another huge shift in the NLP landscape. Just because we went from having to have a lot of supervised data to train the models to having models that perform really well in zero shot or few shot settings. Let me just move this a tiny bit more. Okay, yeah, and when it comes to the research data sets and summarization, currently they span actually many domains, but the majority of research up until recently was done in the news domain, just because it was very, very easy to collect a lot of data in that domain. And some of the representative data sets were either Newsroom or CNN Daily Mail or XSum, which we will discuss later. But as of recent, other data sets in other domains started showing up. So we have data sets in the scientific domain, we have data sets in dialogue. You also have data sets, for example, in the legal domain or long-form narratives such as books. And what all those data sets have in common is how they were created. So most of summarization data sets were created by scraping or reusing web data. And summaries, in this case, summaries are created by using some form of either web page metadata or page headers or post titles. So in many cases, the summaries that we have in the data sets are not kind of human written dedicated summaries, but they are some kind of proxy summary that we train the models on. And sometimes that can be noisy and can cause problems, and we'll also touch on that later. When it comes to evaluation of summarization, the majority of evaluation is done using reference-based metrics, meaning that we need at least one reference summary that we can compare the generated summary to. And one of the most popular metrics here is Rouge, which was introduced around 2004, and that is quite an old metric, and it is based on lexical overlap between the reference summary and the generated summary. And the lexical units that we use here are usually either unigrams, bigrams, or longest common subsequence. And it has been shown that that Rouge has a rather low correlation with human judgments, and there are some other problems with this metric. But despite that, it still is the go-to kind of primary evaluation of those models. And as I mentioned, as kind of popularity of those pre-trained models like BERT, as they were becoming more popular, people started to develop model-based metrics, and BERT score is one of those model-based metrics where instead of kind of having exact token match lexical overlap, we're trying to have this semantic overlap between the generated and reference summaries. And how we compute that is pretty much we embed the tokens from both of those summaries in some vector space, and then we try to compare the both of those summaries, the reference one and the generated one, in some vector space. So the promise of those metrics was, they were promising at first, but then it came out that actually those models such as BERT, the embeddings that they give are not great when it comes to, for example, semantic similarity, just because they're not very sensitive. So we might have one sentence that says, I do have a pen, and one sentence that has, I do not have a pen, even though they have like a complete opposite meaning in the vector space, they would be very close. Again, the promise of those metrics was, they were promising, but now they are kind of considered as secondary metrics. And given that the quality of references sometimes is pretty low in the data sets that we have, people started to move towards model-based metrics that do not require references, and they try to employ QA-based models for that. And in this setting, we usually have some question generation component where that we apply to the source document or the generated summary to generate some questions, and then we apply a QA-based model on those questions and both on the source and the generated summary and compare the answers to kind of establish how good the summary is with respect to the source document. And of course, we also have human evaluations, which have kind of become the standard in summarization. Usually, we just hire some annotators through Amazon Mechanical Turk or some other website, and they usually evaluate summaries across a few dimensions, such as fluency, coherence, factuality, or relevance. And we have briefly discussed kind of the research setting. I'm not sure if there are any questions right now, or if not, then we can move forward. So we've discussed the research setup, and now we'd like to cover some of the existing challenges in the field. And we won't have time to cover all of those challenges, but I would like to talk about one specific challenge, which I think is at this point is very relevant to the field. And it is related to how the task of summarization is currently formulated, and also how the data sets are built. So the challenge that we'll talk about is content selection. And content selection in general is a highly subjective task. And it really depends on the informational needs and the background knowledge of the user of a summarization system. So for example, if we had, all of us were given the same paper and we were tasked to write a summary, all of us would probably write different summaries that would contain different content just because we have different background knowledge. So the current approach to text summarization makes content selection an ill-defined task, simply because there is no one golden standard what should be included in a summary. And how it works right now is we have a source document, we give it to the summarization model, and we expect the model not only to summarize the document, but we also expect the model to know what we want, which I think is a lot to ask from a summarization model or any model. And also how the data sets are constructed does not help, just because usually we have one reference per source document. So it's almost like a setting where we say that each document can be only summarized in one way, which obviously is not true. And because of how things are formulated, the generated summaries do not always contain content that's relevant. So what we really wanted to see is how big of a problem that is, content selection, and how hard is it to kind of find consensus on what is important. So we ran a little experiment as part of one of our papers where we wanted to measure how well humans can agree on what is important in an article. And specifically, this was news articles from CNN. So we hired 5 annotators and we gave them news articles to read, and we tasked them to select sentences that they considered important. And on average, per article, humans selected 2.6 articles as important. But what we really wanted to see is kind of what was the overlap between them. So how much did they agree what is important in a summary? So let's say if a sentence was selected by one annotator, we considered that the sentence got 1 vote. And we wanted to see what was the overlap between the selected sentences. So we considered different vote thresholds. So if a sentence got at least 3 votes from 5 annotators, it was considered important. And in that case, annotators agreed on only 0.6 sentences per article that were important. If we increased the threshold to 4, that dropped significantly to only 0.2. And if we really wanted full consensus between the annotators on what is important, the consensus was almost 0. So pretty much this means that annotators could not agree, even in a simple case of news articles, on what is important. So this again shows that is a highly subjective task. But we also wanted to see whether there's a way to kind of increase this consensus. So we redid this experiment, but this time not only did we show an article to the annotators, but we also provided them with one question. And we said, read this article, this is a question, and select the sentences that are relevant to this question. And in this case, the average number of sentences increased. But what is really important is that also the consensus increased quite substantially for different vote thresholds. And this was especially visible here for full consensus. It was still low, but it was substantially higher than in this unconstrained setting. So we went a step further, and we wanted to really see how would summaries look if humans were tasked to write them. So again, we gave human annotators an article, and we tasked them to simply write a summary. And we noticed that the summaries that they've written, they were kind of like lack direction, and they seem to be longer than necessary. They did cover different content as well. And again, we gave them guiding questions, and we noted that with guiding questions, the summaries were much more succinct, much more to the point, and even though that we initially thought that they would be more extractive, people would just start copying stuff from the input, that was not the case. They were still novel and abstractive. So this raised a question that maybe we should start working on some form of constraint summarization instead of this very generic form of just one article and the model has to figure out everything else. And this leads us to kind of future directions, and a future direction that I'm particularly excited about, which is controllable summarization. And as we mentioned, the information needs for each of the users are different. So again, we have different expectations, we have different background knowledge, we need different summaries. And controllable summarization really allows us to tailor summaries to the individual needs of each of the users. And controllable summarization is itself a blanket term that includes many different subtasks within summarization. So we can have stylistic control, we can have token-guided control, query-guided control, interactive summarization, or personalized summarization. And now if we go through some examples, again, we have the same article about Microsoft purchasing Activision Blizzard. And one example, for example, of stylistic control is that we want this summary to be written in simple English, right? So for non-native English speakers, we might want to use simple English. Or we want it to be casual, or we want it to be like casual English, or we want it to be formal English. When it comes to token-guided control, we can just specify a few tokens of interest, such as FTC, government, antitrust, and we would like the summary to revolve around those tokens. Query-guided control is kind of like a step forward from token-guided control, where we pretty much specify the question in natural language. And this is almost seems to be very similar to abstractive question answering. And actually, the intersection of those fields is sometimes blurry, the line between them. Then we have interactive summarization, where pretty much the user is allowed to interact with the summarization system. So the user can, let's say that the user opens an article and they receive this kind of generic summary that's generated. But then they can click on, let's say, Activision Blizzard, and they get a summary of the same article, but written around Activision Blizzard as this kind of key term. And personalized summarization takes this a step further, where we pretty much in the background somewhere, we build a profile of the user, and we know what the user likes to read, what they read, and maybe some other information, and then we can automatically personalize the summaries for them. And now I'd like to highlight a few of the works that we've done at Salesforce. So this is works that I was part of, and also contributed from some of our external collaborators. So Hydrosum is the first paper, first authored by Tanya Goyal from UT Austin, I believe. And here, pretty much how this project started is that we looked at the summaries generated by summarization models. And we noticed that many of the models, especially the pre-trained ones, fluency and coherence are not a problem anymore. They have substantially improved. And if we look at this article, it's an article about Leonardo da Vinci, and we have a baseline summary written by a baseline pre-trained kind of a fine-tuned BART model. And the summary looks pretty fine. Maybe it is a bit extractive, but what if we would like the summary to be written in a different way? What if we want it to be more specific, or we want it to contain more details, or we just want it to be easier to read? So if we use beam search to decode this summary, we could say, okay, how about we just go down the beam and try to sample a different summary, and that should be substantially different. However, as we went down the beam, we noticed that the summaries were actually very, very similar. So the question was, how do we increase the diversity, right? Since beam search doesn't seem to be helping us in this case. So we took a step back and we looked into the training data for those models. And in this specific case, we used Newsroom as the training model, as the training data set. And we noticed that actually in this training data, we do have demonstrations of those different styles of generation. So we do have summaries that either copy or rephrase. We do have examples that are either detailed or general. And we also have long and short summaries. So the model does have some signal there that it could learn from, yet at inference time, it still decides to simply kind of overfit to one kind of summary that it generates, and it is almost impossible to go outside of that. So the big question is here, since we have the training signal and data, how do we sample stylistically diverse summaries from a summarization model? And the solution that we proposed is called HydraSum. And pretty much HydraSum, what it does, it extends the single decoder of a standard sequence-to-sequence model with a multi-decoder setting. So pretty much, instead of having a BARC model such as here, where we have an encoder, and then we have this kind of like decoder that goes through all the layers and has one generation head. In our setting, we also have a decoder, but an encoder, but the decoder actually has multiple generation heads that can generate multiple probability distributions. And now, if we look closer into this architecture, as I mentioned, we have those multiple heads, and each of the heads does return a full kind of independent probability distribution, and then to actually be able to sample from this distribution, we have this kind of gating mechanism or mixing mechanism that pretty much outputs a distribution over those heads, which we use to mix the heads to obtain the final distribution from which we sample. And now, a few more details about this architecture. Since kind of having multiple heads could substantially increase the parameter size of the model, which is maybe not preferable, maybe would not be a fair comparison with other models. So to reduce the number of new parameters in the model, what we did is we have a fully shared encoder, and we share most of the layers of the decoder. So really what we have is only the last few layers of each of the individual decoders are kind of customized to that specific decoder. And we also have the gating mechanism here, and how it works is that it takes the hidden state of the last shared layer of the decoder, and then we have just a linear transformation here in a softmax to get the distribution over that we will use to kind of mix those individual distributions. And now, when it comes to training, there's two ways of training those models. One is a standard training procedure where we use standard cross-entropy loss. And in this case, no data pre-processing is necessary. And what is really cool about this is that actually this stylistic partitioning that we'll see later, it kind of emerges naturally. The model just learns it itself. So what we've done here is obviously before we started training, we initialized the model with one of the pre-trained checkpoints, and in this case, we've used BARC large, and here we've even initialized all of those individual heads with the same parameters. But the only thing that was random before starting training is that we randomized this weight matrix W, so that once we start training, all of those are the same, and they might initially return the same distribution, but the mixing coefficients will be different. And at that point, from the very beginning of training, the gradients will flow, different gradient information will flow to each of the heads. So this is standard training. And we also have forced partitioning, where pretty much we can manually allocate the styles to specific heads of the model. And in this case, we have to do some pre-processing, so we pretty much have to take the data sets and bucket the examples according to some traits that we want to have. So, for example, we can have some examples in one bucket will be very long, and the other bucket will be very short, and the third bucket will be very abstractive, and another one will be very extractive. And then we pretty much force the model to learn by supervising the gating mechanism. So let's say if bucket 1 was long summaries, then we would just set the gate to 1 for all the long summaries, so that only this one decoder learns the long summaries, while let's say only this decoder would learn short summaries, and so on. And when it comes to inference, we have 3 ways of sampling from this model. So one of the ways of sampling is pretty much sampling from individual decoders. So we can do, this is an example with 2 decoders, but obviously this scales to more. But we can sample from individual decoders just by setting a hard hard gating mechanism, so 1 and 0s for the rest. We can have a mixture of decoders where the gating mechanisms decide what is the mixture. So pretty much the model not only outputs the probability distributions, but it also outputs this kind of mixing distribution, and the model decides what stylistic features it wants to use for a summary. Or we have this third model where we can manually kind of set the mixing distribution and decide ourselves what stylistic features we want to sample from. And how we evaluated this model is that we evaluated on 3 data sets. All of them were in the news domain, but despite that, they do have widely different characteristics. So for example, CNN Daily Mail is known to be a mix of abstractive and extractive summaries. So is Newsroom. But for example, XSum is known to be an extremely abstractive data set. And here we compared the 2 heads. So those experiments are on HydraSum with 2 heads, but in the paper we also have experiments on 3 heads. So here we compared the 2 heads, D0, D1, and a mix of those 2 heads with a reference summary and the baseline. And the baseline was a regular BART model. And then we look into multiple dimensions that we evaluate across. So we have abstractiveness, which is evaluated in 3 ways. We have the coverage score, which in our case the coverage is the fraction of summary words that are also in the input. We have a density, which is pretty much the average length of a span that's extracted. So pretty much the lower density, the more abstractive the model. And we have a simple 2-gram overlap, so a bigram overlap between the input and the summary. Then we have specificity, so how general the summaries are, and this was evaluated using a dedicated model called SpeciTeller. We have length metrics, so absolute length, and also compression ratio, so pretty much the ratio of summary length to article length. And we have the readability score, which was evaluated using the Flesch readability test, which is a test in linguistics that pretty much evaluates how easy it is to read a text. And here we notice a few things. So first of all, the 2 heads, and those are I'm not sure if you can see if it's gray, but like the highlighted examples here are examples where the differences between the 2 heads are statistically significant. So we see that for CNN and Newsroom, both the abstractiveness and specificity, the difference between the heads is statistically significant. So they were like substantially different in how they generate. For Newsroom, for CNN, we also see that the models learn to diversify the length and the readability. And one surprise here was that for XSum, there was actually no difference in abstractiveness, but I think this actually made sense given how little diversity there is in abstractiveness in the reference summary. So there was just not a lot of signal in the data itself. But specificity is still different here. So pretty much this shows that the combination of stylistic features that the model learns pretty much heavily depends on the features that we can find in the data sets. And now kind of looking into zooming in on the CNN and newsroom data sets and comparing kind of the distribution of abstractiveness, both of the reference summaries and the baseline. And we see that the reference summaries for both for CNN and newsroom, they kind of have this almost like bell curve distribution over the abstractiveness, right? So we have a bit of everything, but many of them are kind of in the middle when it comes to abstractiveness. However, the baseline model just learns to be very extractive, right? So we see that distribution is like completely off and not even similar to what we actually want to learn. And this kind of makes sense because in summarization in other works, people have noticed that pretty much models tend to over-rely and overfit to the extractive examples just because it's so easy to learn to copy instead of generate itself. So models overfit to extractive examples and they just kind of learn to ignore the abstractive ones. But now if we compare our hydrosum model to this, we see that in case of CNN and newsroom, the D0 head, so the first generation head, actually has a distribution that is, in this case, is like much closer, and in this case is also closer than a baseline. And then we have the second head is kind of the extractive head that pretty much does similar to the baseline. But we see that we already like sampling between those two heads, we can actually cover a much wider range of abstractiveness than we would with a baseline model. So here are some examples of the generated summaries. So in the first example, we have quite a few differences when it comes to abstractiveness. So we see that the D0 summary is quite abstractive, that there's very little copying, whereas head D1, the underlying text is pretty much all copied from the source. So we see that the summaries are quite substantially different, even though they do cover the same topic. And in the second case, we have specificity, where we see that D0 is much more specific, so we have more details in the summary than we would have in the summary generated by head D1. And so far what we've done is we allowed the model itself to decide on how it mixes the outputs, but we can also manually set. So this is the third type of generation that I mentioned before, and we can kind of manually mix how we want to generate. So in this case, we again have abstractiveness and specificity, and those are the two extreme partitioning case. So this is like generating only from head D0, and this is generating only from head D1. And we see that the distributions, for example, for abstractiveness, it's not that bad, but here D1 is, it's pretty off. But so let's say that we decide to mix the heads 50-50, and we see that for example, specificity almost gets like a perfect fit with the reference. The abstractiveness here, it kind of slides tiny bit from being like extreme. It kind of slides slightly towards a better distribution. But we can also try different mixes. So we can try a 0.5 or 0.7, and we see that pretty much we can interpolate between those two extremes however we want. So to wrap this part, we pretty much we introduced hydrosum, which gives us stylistic controls over sequence-to-sequence models. And what is cool is that the models can learn automatically to assign those stylistic features to the individual heads. Inference is highly flexible, so the model can decide for itself how it wants to generate, or we can tell the model how to generate. And also, no manual data annotation was necessary in this case. And I'm not sure if we should take any questions with respect to hydrosum, or we should go further. No questions? Okay. So the next paper I'd like to highlight was what's new, summarizing contributions in scientific literature, and this was work with Hiroaki Hayashi, who actually has joined Salesforce Research after completing his PhD. And in this work, so far we've shown that we're able to gain stylistic control over the generated summaries, but in this work we decided to focus on summarizing scientific documents. So here we have an example of an article that describes some HVAC systems, and I believe it was a machine learning paper, so it was kind of like reinforcement learning for managing HVAC systems. And we see, again, a summary that's generated by a baseline kind of not controlled model, a BART model, and it seems to be a fine summary. However, again, if we look closer, we notice that really the summary is a mix of kind of a lot of things. So it's a mix of kind of background information, it's a mix of contributions, so we have some like background and problem statements here, it has some contributions over here, so there's a lot, and it also seems to be a very long summary. So there's really no way for us to control the content of the summary. And this is partially due to how we approach content, scientific paper summarization. So how it works these days is that we have an article and we treat the abstract as a summary and we try to generate the abstract, right? So this is kind of what I said before about data sets. Many of the references are proxy references. So I'm not really sure if an abstract is a good summary of a scientific paper. Probably not. Just because abstracts, they contain a lot of information. So they contain, again, the contributions, they contain some some context, and they also contain some kind of fluffy sentences just to make it more readable, right? So there's a lot in there. And the second thing is that a lot of, or pretty much these days, most of scientific papers already come with an abstract. So there's really no use of trying to generate a new abstract because we already have one. So what we really want from a summarization paper that works on scientific papers is to kind of quickly and efficiently, to be able to quickly and efficiently read and understand the contributions of a paper. And again, we step back, looked at the data, and here we've been working with this data set called S2Org, which is pretty much a data set that was collected from arXiv and the other repositories. And we wanted to see whether there was actually some training signal there that we could use to build a model that would be more controllable. And here we notice that there actually is. So a lot of the abstracts, again, contain information about the background for the paper. They contain some information about the context and some fluff, which is maybe not that useful. So now the question was, how do we train and sample summaries that can actually, where we can control the content? And in this case, we introduced a whole new task. So we introduced the task called disentangled paper summarization. And here the goal was to generate more focused and useful summaries of scientific papers specifically. So how we approached this problem is that we said that instead of generating one summary that's very general, we'll generate two summaries that are more specific. So one summary will contain the contributions and only the contributions of the paper, and the other summary will contain the context of the paper. So any background knowledge that we might require to understand the paper. And alongside the task, we also introduced two models. So one is a multi-head model, which you can kind of find familiar from HydraSum, a lot of shared layers and two kind of individual heads that generate. And we also have this standard sequence-to-sequence model with token control, which pretty much was a single model that takes an input, and this input also has a control code prepended to it, and the control code was either contribution or context. And based on this control code, the model will generate either a contribution summary or a context summary. And now looking closer into the architectures, again, the multi-head architecture, very similar to HydraSum. We did have shared decoder parameters to reduce the model size, but here there's two generation heads. They worked independently, so there was no mixing between them because we wanted to have separated summaries. When it comes to the control code model, again, all model parameters were shared, and the only control came from a control token that was prepended to the input. And when it comes to training, we use standard cross-entropy training. So again, nothing crazy here, but the data did require some pre-processing. So at first, what we did was we manually annotated abstracts. So we selected sentences from abstracts that contained either contributions or they contain context. And we annotated 400 abstracts like that, which gave us about 3,500 annotated sentences. And then we trained a sentence level classifier on those annotated examples. And the classifier was pretty much tasked to, given an abstract, it was tasked to classify whether a sentence was a contribution, context, or nothing. And the classifier that we trained had an accuracy of 86%, which is relatively high. And we used that pre-trained classifier to kind of generate a silver standard model, silver standard data, which we used for training the actual summarization models. And inference, again, nothing crazy here. Standard decoding for the multi-head model, and just prepending the control codes for the control code model. Alongside the models, we also introduced this kind of a very detailed way of evaluating the models. So we had three kind of metrics here. One was relevance, which were pretty much relevance. We compared the generated summaries. So this is a contribution summary, this is a context summary, and we compared them with their respective reference summaries. So this is a reference contribution, reference context. We have the purity, where pretty much we want a generated summary to be similar to its own reference summary, but I want it to be also far away from the opposite summary. And we also have a disentanglement metric, which pretty much measures how close those two summaries are, and we want them to be as far as possible. So we want them to have as little overlap as possible. And the first experiment that we've run here was to see whether either of those models is better, right? So we wanted to see whether the control code model was better or the multi-head model was better. And from this experiment, we've noticed that generating context seems a bit easier than generating contributions. And this might be just the fact that we hypothesize here that just possibly the language used for describing context might be more standardized than the language for describing contributions in papers, especially that we've worked with many domains, not only kind of computer science, but also medicine. And for example, in medical papers, the contributions are usually just some like statistics. So that was our hypothesis here. Apart from that, the models perform pretty similar, both in relevance and purity. But we've noticed that the control code model performed quite better when it comes to disentanglement, which was surprising given that we thought that maybe having dedicated generation heads would be more helpful. Apparently it wasn't, so that was something that we've learned. And now a more exciting experiment than this is that we took this control code model and we really wanted to see how this would perform in a real world scenario, right? Because we want these models to be useful. So we created a human study that involved expert annotators, and the expert annotators were actually people who had PhDs, so they were kind of familiar with the paper review process. And we created this kind of artificial paper review setting where we said, okay, here's a paper, and imagine that you have to review this paper. And along the paper, we provided them with two summaries. And one summary was generated by a regular summarization model for paper summarization. And another summary was this disentangled summary that we generated with our models. And we asked them, which of those two summaries is more helpful for you to review the paper? And we conducted this study on two data sets, so the S2ORC and also kind of like a core data set, which was medical data related to COVID. And in both cases, 77 and 81% of the experts said that, or 77 and 81% of all the experiments, annotators said that the disentangled summary was actually more helpful in summarizing than the old-fashioned summary, abstract-based summary. So this was very promising that maybe the models themselves are not perfect, but they are already helpful for reviewing papers. And here we have some examples of the generated summaries. So we see, again, this is the HVAC paper. General summary mixes a lot of things, seems to be very, very long. But the contributions seem to be, together they do seem to be almost the same, like maybe a bit longer. But for example, if you are an expert in the field of, RL for HVAC management, you just have to read the contribution section and you don't have to really read the context. So Here we introduce the task of disentangled summarization, which adds control knobs for content selection. We introduce two models that are able to generate distinct summaries, and we unfortunately kind of the control dimensions have to be defined before training, and minimal data annotation is necessary in this case. And one more work that I'd like to highlight in this case is control sum, and this is also work in collaboration with Jin He, who recently graduated from CMU, and also my colleagues at Salesforce. And so far we've kind of shown that we can develop models that give us some control over the stylistic features, and we can generate models that give us some control over the content. However, kind of in both cases, well, in the case of HydraSum, the model kind of automatically learned the stylistic features that it would allow us to control. And in the case of disentangled summarization, we had to predefine the control aspects, right? So this is a separate case, and we're going back to new summarization here. So we have an input article about some basketball games, and again we have a summary generated by a general model, and the summary kind of covers, it covers some details from the Miami Heat game. It also mentions some other teams that won that day. However, let's say that what if I'm a Golden State Warriors fan, or what if I want stats about a very specific player, right? So the generic summarization model, or the models that we've introduced before, they don't really give us fine-grained control, and they don't allow us to say, like, I want this specific player, I want the summary to be specific on, I want the summary to be focused on this specific player. So in that sense, they're pretty inflexible. And also, we can't really anticipate all the user's needs ahead of time, right? We can't generate a HydraSum model that has, I don't know, like 1,500 heads that will kind of cater to all the needs of potential users. So that doesn't really scale well. So again, we look back into the training data, and this is news data again, and we see, is there a signal for us to kind of use this data to train a model that will give us fine-grained control over the summaries? And again, we notice that there is, because the summaries in that data set actually cover many entities, they have different perspectives, so there is signal there that we can learn from. So now the question was, how do we sample and build a model and then sample from a model that will give us a very fine-grained level of kind of control over the content of the summary? And in this case, what we proposed is control sum, which is a generic framework for fine-grained control and summarization. And what is interesting is that this framework is model agnostic, so we really can apply it to any model, and it really heavily focuses on how the model is trained. And our primary focus here was entity control and length control. And on a high level, how this model works is that we have a user, and the user specifies a list of tokens or a list of named entities that they're interested in, and this list of entities kind of guides the generation process. So it tells the model what content should be in there. And the user interacts with the model through a control function. The control function on a very high level pretty much just takes raw tokens from the user, and it reformats them into a format that the model understands. So there's kind of like no magic there. And again, looking closer into the architectures, on the architectural side, there was really no fireworks here. It's agnostic, so we can apply it to any model we want. In our case, it was BART large. But training required some pre-processing, and it was also done on kind of standard cross-entropy loss. So the pre-processing that we had to do is we had to look into reference summaries of the data, and we had to identify terms of interest. And we cast a very broad net here when it comes to terms of interest, and we said that those are really any phrases that are not stop words, so very broad. And then we extract those terms, and we prepend them to the very beginning of the document. And one more pre-processing we did, we actually bucketed the examples by length and the number of tokens that we have prepended as the kind of control code. And then we just trained, using this kind of simple pre-processed data, we trained the model, and the model automatically learns how to associate the presence of entities in this kind of control list with their presence in the source document, and then with their presence in the reference summary. So it just learns that if I see a token prepended to the document, I should probably write a summary that's related to that token. And it also learns to automatically kind of associate the number of tokens that we specify with the length of the summary. So if we give it fewer tokens of interest, the summary will be shorter. If we give it more, it'll be longer. And when it comes to inference, there are a few ways of kind of controlling those models. Alongside the main summarization model, we trained also a kind of automatic key phrase extractor that would assist the user with finding important entities. And having this model, we could kind of run inference in multiple ways. So it could either be like model controlled. So the model would select the tokens of interest and then summarize the document according to those. We could have a partial user control where the user would collaborate with this key phrase extractor to choose the tokens, or we could have full user control where the user just specifies the tokens that they're interested in and the model generates the summary for them. And here we have two experiments. So the first experiment that we've run, we wanted to see how the model really responds to entity control. So whether the model actually learns to output or summarize or include the tokens of interest in the summary. And here we have a metric which is called the success rate, which is pretty much the fraction of summaries that actually mention the entity that was given as a token of interest, right? And how we've run this experiment is that we took all the entities that were given in the source document, and we just kind of we generated kind of permutations of those entities. So we would have each example would have kind of we would dissect, I guess, each source document into multiple examples with different entities prepended, and then we would check whether those entities also occur in the generated summary. And if they did, then we had a 1, and it was kind of a success. And here we also separate this into two numbers. Lead 3 is where the entities were taken from the first 3 sentences of the article or from the full article. I just wanted to make sure that the model doesn't overfit to the beginning of the article. But we not only are interested in the success rate because the model could easily learn how to cheat and just output a bunch of tokens and nothing else. So we also want to make sure that the quality of the summary is good. So we do care about the factual correctness, and we did have human annotators evaluate our summaries. And in both cases, we noticed that in comparison to baseline models, control sum actually outperforms them quite substantially in all the settings. So it does respond very well to entity control, and it also generates factually correct summaries. So pretty much it says that when it comes to entity control, control sum has learned that from the training procedure. And the next thing we wanted to check is length control. So again, how the model responds to length control. And here we ran the study on 2 data sets, so CNN Daily Mail and XSum, which we mentioned before, and we have 2 metrics. So this metric is kind of the deviation of the output length from the reference length. So pretty much we want the reference length and the output length to be as similar as possible. And the second one is the correlation between the token of interest list and the output. So we want pretty much the more tokens we give as input, the longer we want the output to be. The less the tokens of interest we give as input, the shorter we want it to be. And again, we see that in both cases, this metric, the lower the better, this metric, the higher the better. In both cases, control sum actually performs better than one of the baseline models, and it actually has, in both cases of both of those data sets, it actually has quite good correlations. So conclusion here is that it does learn to respond to length control. But one last thing that I wanted to mention is that as we were playing with those models, by default they were supposed to just respond to token control. But just for fun, we decided to give the model a natural language question. So we said, okay, how many scores did Steph Curry get? And we noticed that actually the model, even though it wasn't trained to respond to those queries, it did learn that. So it did have like this emergent ability to handle natural language questions, which was quite surprising and also a really cool finding. So once we noticed that, we said, okay, well, let's see how it performs in zero-shot performance on QA datasets. So we took a used QA dataset, we took the squad dataset, and we compared our control sum with other models in a zero-shot setting. So we used GPT-2 large, BART in both settings, and we see that it quite substantially outperforms all the baselines in zero-shot performance. And while it's not as good as some of the supervised models, it's also, it's not that far, at least from the LSTM one. So here are some examples. We've run this on QA length and entity control. We have contributions of papers. That's also an experiment we've run. And we also have patent data. So we have like the purpose of the patent, for example. And those two are kind of things that we were hoping we would get. And all those three categories are something that was just emergent ability. So this is something we discovered as we were playing with the model after it was trained. So to wrap this up, control sum adds fine-grained control when it comes to the content of the summary. Some pre-processing is necessary, but it's done automatically, so it's not that intrusive and can be done really quick. And control sum actually did show emerging abilities that we were not planning for. So in this presentation, we've discussed what is text summarization, what are the approaches to text summarization, and what are promising future directions. We've discussed controllable summarization, and I think that first of all, when it comes to, I would encourage all of you, if you're interested, all those three papers that I mentioned, they do have more experiments, so it's worth checking them out. But for future work, I think that first of all, dedicated datasets for controllable summarization are an important direction, just because we've shown that without dedicated datasets, we can go quite far when it comes to control. But if we had some dedicated data, we could go even further, I believe. So that's the first thing. And the second thing is that really without good metrics, we can't make progress. So if we can't really evaluate how good our models are, we won't be able to say what are the downsides of the models, right? So I think building dedicated evaluation metrics for content selection and controllable summarization is also a very important direction for research. And I think that once we have those two covered, then summarization will progress really fast from there. So are there any questions for discussion?
Pytania, przemyślenia, coś ma do powiedzenia. Nic zupełnie, wszyscy zostali zastrzeleni. Piotrze.
Ja mogę mieć takie techniczne pytanie,
Tak.
bo jak mamy w tych modelach takie streszczenie, że Warszawa jest stolicą Polski i dostajemy zdanie, że Warszawa nie jest stolicą Polski,
Tak.
to jak to jest właśnie? Jak sobie radzimy z takimi przykładami?
Tak, to jest ciekawy temat. Ja też mam paper związany z tym. To jest taka cała dziedzina, powiedzmy, jeżeli chodzi o ewaluację streszczania, to jest, nazywa się factual correctness i faithfulness. Niestety nie było czasu, żeby dzisiaj to przedstawić, ale są modele, które też starają się właśnie tego typu rzeczy sprawdzać, tak? I te modele albo są właśnie QA-based, albo są modele takie based na modelach NLI, czyli Natural Language Inference, gdzie bierzemy zdanie, każde zdanie wygenerowane z tego streszczenia i porównujemy z każdym zdaniem albo z całym, powiedzmy, tym źródłem, albo z każdym zdaniem z źródła, no i próbujemy zobaczyć, czy tak jakby to się zgadza, czy nie. Tak więc to na pewno jest problem, więc to jest jeżeli chodzi o ewaluację tego, a jeżeli chodzi o, powiedzmy, jakieś na poziomie tak modelowania, żeby to naprawić, to też są różne taktyki, tam jest, prawda, pre-training, taki ludzie robią, żeby to factual correctness było lepsze, ale też są takie modele, które robią rewriting, tak? Czyli mamy wygenerowaną streszczenie i potem mamy taki rewriter, kolejny model, który tak jakby bierze znowu to streszczenie, bierze znowu źródło i w razie czego poprawia błędy. Czyli tak.
Masz jeszcze przemyślenia? czy nie?
Czy to się da tak bezpośrednio zaadaptować do innych języków? Czy w ogóle robi się z innymi językami, czy po prostu się tłumaczy to później?
To jest dobre pytanie. Wydaje mi się, że no wiadomo, że jeżeli chodzi o angielski, to jest najwięcej danych teraz, tak? Ale po pierwsze pojawiają się zbiory danych w innych językach i też pojawiają się zbiory danych w takie multilingual zbiory danych i na przykład tutaj jest jeden gość, który mam w referencjach, ten Thomas, on wydał paper, który jest właśnie multilingual summarization dataset. On jest w tym FAIR, Facebook AI Research w Paryżu.
Biorąc pod uwagę, jak dobrze działa GPT na innych językach, na przykład angielskim, no to czy w ogóle ma sens budowanie zbiorów danych dla innych języków, czy po prostu wystarczy tłumaczyć? Chcemy mieć streszczenie, nie wiem, tekstu polskiego na angielski, no więc nie wiem, przetłumaczymy sobie to na angielski i streścimy. I mamy już wszystko gotowe.
No tak, no to prawda, to znaczy to zależy... To zależy, jaka jest jakość modeli tłumaczenia, tak, jaka jest jakość modeli streszczania, bo jeżeli powiedzmy zaczniemy sobie taki łańcuch modeli robić, tak, to możemy mieć nagle taki error propagation, tak, po prostu, że no właśnie. Więc...
Nie może od razu wszystkiego zrobić. Słuchajcie, nie macie takiego wrażenia, że to się wszystko po prostu zbiega do jakiegoś jednego wielkiego muszczku, który robi wszystko dla wszystkich języków i właściwie, no nie, no ja akurat na swoim tam warsztacie kiedyś miałem Idona, takiego gościa z Izraela, wykład zaproszony o wielodokumentowym streszczaniu. No i to się jakby, no mi się to skojarzyło, tak, że teraz jakby wrzucić wiele dokumentów, to ten model też by sobie tam poradził, prawda, z tym wszystkim. Że to dwa zadania, które były przez wiele lat osobne, to teraz się jakoś zbiegły w jedno zadanie. I właściwie wszystkie zadania nam się NLP zbiegają do jakiegoś jednego modelu, który będzie to wszystko robić. Czy nie właśnie?
Znaczy, wydaje mi się, że osobiście, jeżeli chodzi na przykład takie streszczanie wielu dokumentów, tak, no to wydaje mi się, że takim znowu jeżeli damy modelowi tak kilka dokumentów, niech to będą artykuły takie zwykłe z gazety, tak, damy mu kilka artykułów, no i powiemy streszcz to, tak, no to ten model może mieć problemy, bo na przykład może być kilka takich case'ów, jeżeli chodzi o te artykuły, tak, wszystkie artykuły powiedzmy mogą mieć tą samą perspektywę, no i wtedy tak jakby ten model jedyne co musi zrobić to tak jakby duplikacja faktów i streścić jedną perspektywę, tak? Ale może być inny sposób streszczania, jeżeli mamy powiedzmy skrajnie różne publikacje, tak? Mamy jedną bardzo konserwatywną, drugą bardzo liberalną i jest na ten sam temat się wypowiadają, tak? No to wtedy ten model nie tyle musi robić te duplikacje faktów, co musi tak jakby je porównywać i wtedy ten model musi wygenerować bardziej takie źródła odniesienia, tak? Czyli powiedzmy ta strona, czy ta gazeta mówi to, ta gazeta mówi to, tak? Więc to jest, ten output będzie inny.
Może mi się skojarzyło dlatego, że tam właśnie w tym wykładzie on też mówił o dokładnie tych samych rzeczach, że o takim streszczeniu, że tam, nie wiem, czy to w ogóle można nazwać streszczaniem, ale chyba to wciąż jest multi-document summarization, więc o zadawaniu pytań dotyczących właśnie jakichś faktów, które się w tych wielu dokumentach pojawiały, albo właśnie o tworzeniu streszczenia, które jest tak ukierunkowane jakimś keywordem, tak jak to tutaj było. Dlatego mi się to skojarzyło. I zastanawiam się też, jak właśnie modele językowe, które gdzieś tam w sobie jakąś wiedzę już mają się do tego, bo jeżeli w dokumentach nie jest powiedziane, że Warszawa jest stolicą Polski, no ale to byśmy chcieli jednak, pytając o jakąś konkretną rzecz, na przykład o Polsce, a tam będzie napisane, że w Warszawie coś się działo, no to dostać tę odpowiedź. Jak to się, dlatego mi się to wydaje, że wszystko jakoś tam się zbiega. Nie wiem, czy tędy droga, no bo te modele, a właśnie, no jakby nie wiem, no po prostu GPT-3 użyć do tego, co tutaj...
Używamy, znaczy będziemy mieli parę paperów związanych z GPT-3 i właśnie jedna z naszych tutaj, ta pierwsza autorka Hydra, sam Tania Gojal też miała ostatnio właśnie GPT-3 w streszczaniu wiadomości, no i performance jest bardzo dobry. Ale to też jest właśnie, to jest ciekawe, trochę tak jakby połączenie tych tematów, tych modeli językowych i tam jeszcze to, co Pan pytał, jeżeli chodzi o ten factfulness i factuality, tak, że zauważyliśmy, jeżeli chodzi o streszczanie tekstu przynajmniej, że jeżeli w tych starszych modelach typu LSTM, które nie były trenowane, tam pre-training nie był, tak? To te modele robiły dużo takich błędów, które się nazywały intrinsic errors, tak? Czyli to są błędy po prostu niezrozumienia źródła, tak? Czyli po prostu, no nie wiem, jest wywiad z kimś, tak? I ta osoba jest mężczyzną, a model mówi, że jest kobietą, tak? Albo na odwrót. Ale to jest tak jakby po prostu niezrozumienie źródła. A teraz modele, które mają wiedzę w sobie, często jeżeli nie wiedzą co powiedzieć, to zaczynają kłamać i wymyślać, tak? I to jest ten problem właśnie. I jeżeli chodzi właśnie o streszczanie, wydaje mi się, że no tak, jest potencjał w tym, tylko że te modele językowe muszą być update'owane, tak? Bo powiedzmy, jeżeli mamy teraz, no nie wiem, Trump był prezydentem, a teraz jest Biden, tak? No to ten model musi być zupdate'owany, musi zorientować. I teraz jest kolejny krok, który to nie, był research związany z tym i wydawało mi się, że to będzie taki dosyć mocny nurt, ale GPT to trochę zabiło. To było to, żeby robić takie modele retrieval language models, tak? Czyli to są modele, które mają dostęp do jakiejś bazy wiedzy i one mogą generować tekst, ale mogą zawsze sobie zajrzeć do tej bazy wiedzy, tak? I to jest wtedy łatwiej jest to update'ować, bo powiedzmy możemy sobie wziąć jakiś, nie wiem, zbiór krotek, tak? Z wiedzą. No i ten model sobie generuje, ale jak czegoś nie wie, no to patrzy sobie do bazy wiedzy, gdzie ma zaktualizowaną bazę wiedzy, tak? I może sobie generować dalej. Więc to jest, wydaje mi się, że łatwiej to update'ować w ten sposób, niż, nie wiem, robić fine-tuning takich gigantycznych modeli jak GPT-3 na przykład.
Kurczę, się wszystkie kraje na świecie skipnęły i zrobiły taki jeden globalny model.
To była inicjatywa, jak to się...
Że to nie, to jest nierealne, ja wiem, no tam jakaś wielka, ale no lepiej oczywiście wrzucać tam rakiety na sąsiednie państwo.
Ale była ta inicjatywa Big Science, nie wiem, czy Państwo kojarzycie to. To była inicjatywa taka, tam było chyba, wydali paper, na którym na listę autorów, to było nie wiem, chyba z 200 albo 300 autorów. I to było dużo uniwersytetów z Europy to robiło i oni właśnie wydali model, który jest takim konkurentem do GPT-3, tam on się nazywa Bloom chyba. I to jest model, który jest multijęzykowy, open source'owy i Hugging Face między innymi było tak jakby jednym z tych key contributors powiedzmy w tym researchu. Ale są takie, no więc może to nie jest jeszcze ta skala, ale wiem, że są takie ruchy i wiem, że też dużo europejskich uniwersytetów i tam były jakieś granty, a więc ta infrastruktura obliczeniowa też była tak jakby dosyć mocna w tym.
Nie, o tym nie słyszeliśmy. Myślałem, że OpenGPT X-ie chyba, tak? To słyszeliście pewnie, że... No ale dobra, no, że to już dobrze. Ktoś ma coś konkretnego, co zapytać dużo? No, moje pytania są niekonkretne zawsze.
A jak na przykład jest do streszczenia taki dokument, bo wyobraźmy sobie, że mamy książkę, w której na przykład, nie wiem, jest jakaś akcja, dialog, rozmawiają dwie osoby i rozmawiają o czymś zupełnie innym, to czy na przykład treść takiej rozmowy też się streszcza?
To jest właśnie dobre pytanie i tutaj mamy, to też nie udało mi się o tym powiedzieć, ale ja wydałem paper, w którym to roku było tutaj Boxam, tak? I to jest właśnie zbiór danych, jeżeli chodzi o książki. I my niestety tak jakby, no te książki były bardzo długie, które tam mieliśmy w tym zbiorze danych, więc my to taką mieliśmy w sumie dosyć proste podejście, bo skupiliśmy się głównie na streszczaniu rozdziałów książek, tak? Ale wiem, że OpenAI, potem współpracowaliśmy z nimi i OpenAI zaaplikowało ten swój, może nie wiem, czy to chyba nie był GPT-3 jeszcze, ale to był ten, powiedzmy, GPT 2,5, zaaplikowało do tego zbioru danych i oni to robili w taki sposób hierarchiczny, tak? Czyli powiedzmy streszczali cząstki tego tekstu, potem z tych streszczeń cząstek streszczali kolejne i takie drzewo się robiło aż do pełnego streszczenia, czyli w odpowiedzi oni to robili bez jakiegoś, powiedzmy, znajdywania na przykład dialogu i streszczenia dialogu i potem streszczania reszty, ale wydaje mi się, że jest to obiecujący kierunek.
To jak to w paragrafach? Czy
oni w paragrafach to robili, tak. I tam oni to robili nawet paragrafy, głównie skupili się na tym, żeby nie były koniecznie jakoś semantycznie te paragrafy rozdzielone, tylko chodziło o to, żeby ten input, rozmiar inputu się zgadzał.
A to były książki naukowe czy beletrystyki?
Nie, to są książki ze zbioru Gutenberga, czyli to są książki, do których copyright wygasł. Czyli to są, tak, czyli beletrystyka.
bo powieści beletrystyczne charakteryzują się główną różnicą w stosunku do noweli, że są wielowątkowe. I te wątki się plotą przez całą drogę. Stąd moim zdaniem najciekawsze by było wyłapanie poszczególnych wątków i streszczanie ich jako całości.
Tak, i wiem, że jest też taki research, to jest to już jakiś czas temu to się działo, to jest jakieś śledzenie tak jakby, to się chyba nazywa jakiś tam temporal tracing, nie aktorów, tylko może tych bohaterów książek, tak, że jest każdy bohater, powiedzmy, ma swój jakiś tam stan i tak jakby, tak jak idziemy przez ten tekst, to postaramy się śledzić jego stan i tam z tym działać, więc może to rzeczywiście byłoby ciekawe podejście.
Tak, ale tutaj jeszcze trzeba było popatrzeć na interakcje, sieć interakcji bohaterów, żeby wyłapać wątki tematyczne.
Tak, no to na pewno było ciekawe, tylko to też by zależało dużo pewnie od jakichś modeli takich pośrednich, prawda? Więc znowu jest ten problem tak jakby propagacji błędów, który mógłby nastąpić, ale na pewno jest to ciekawe rozwiązanie. I też jakieś budowanie grafów i potem na podstawie tych grafów streszczanie tego.
Ten model by sobie poradził, jak się jako keyword wykonał nazwisko tego bohatera.
Myślę, że na pewno by jakieś streszczenie by dało, ale pytanie, czy by było dobre. Tak.
Wątek to jest trochę co innego niż co robił bohater. Ale nie, co robił bohater to jest po prostu inny trochę problem, równie też ciekawy.
Tak, znaczy to jest... Jeszcze w książkach jest ten problem, że może być na przykład retrospekcja, tak? Co już jest zupełnie tak jakby, jeszcze w czasie mamy te wątki poprzestawiane, no i wtedy to już jest zupełnie tak jakby inny poziom.
Temat rozmowy, który może dotyczyć rzeczy przeszłych.
Tak. No tak, to jest, akcja się dzieje teraz, ale...
Jest to do zrobienia jeszcze, tak.
Co oczywiście są pewne słowa kluczowe, czyli właśnie takie czasowe, sugerują. Pamiętam jakoś.
Dobra, no to zaczynamy dryfować, także dzięki.
Booksami jest dostępny, są skrypty do ściągnięcia dostępne bo przez copyright wiadomo nie mogliśmy, znaczy książki są dostępne, a same streszczenia są skrypty do ściągnięcia tych streszczeń. Tak. I też zachęcam, w tym roku organizowaliśmy z paroma osobami z Kolumbii, z Amazona taki warsztat na callingu, nazywa się Creative Sum i tam było właśnie streszczanie książek, streszczanie takich różnych skryptów filmowych i tego typu rzeczy. Generalnie to było creative writing, które próbowaliśmy streszczać. To jest benchmark, który jest związany z tym, więc można zajrzeć, nazywa się to Creative Sum.
Będzie nowa edycja?
Staramy się dostać, chyba nas odrzucili z ACL-a w tym roku, ale będziemy pisać rebata, więc może się uda.
Aha, ale warsztatu edycja?
Warsztat, tak, znaczy próbowaliśmy robić kolejną edycję warsztatu.
Teraz już przyszły jakieś tam...
No właśnie, więc tak.
Chyba odrzucili.
Tak. Spróbujemy.
Dobra, dzięki.
Super. Dziękuję bardzo.
Tak, nie wiem co mamy w przyszłym roku. Na początku chyba mamy coś zaplanowanego, ale już zaraz zajrzę. Nie, teraz 9 czerwca, możemy to jeszcze nie wysłano
Będzie jakiś ten...
slajdy, właśnie.
Slajdy tak. Muszę to może mailem je prześlę tylko.
Tylko pracę tam patrzę się, tam odpowiadane to moje pytania, też tam będą.
Jest chyba zacytowane. Znaczy, bo generalnie tak, jeżeli chodzi o streszczanie tekstu i to factuality, no to ten paper, który ja wydałem, to był jeden z pierwszych, jeżeli na ten temat. On się nazywa tam Evaluating Factual Correctness in Text Summarization. Więc to było pierwsze i potem było dużo follow-upów do tego, więc tak jakby ja korzystałem, to był taki dosyć prosty sposób używając modeli takich NLI do tego, a potem się pojawiły te modele QA, potem ludzie znowu wrócili do NLI, więc na pewno był progres zrobiony w tym. No, to myślę, że to jest dobry start i potem po prostu prześledzić sobie cytowanie i będzie więcej tych prac.
Okej, dobra, dzięki.
Bardzo dziękuję też.
Tylko było to w moim może kurczę, ale
nie wiem, to będzie, no najwyżej on drugi raz wydrukuje.
Dobrze, nie zobaczę. Czasami mam wrażenie, że Ela coś wyjmuje i rozdziela po ludziach, gdzie jeszcze oni są dużo... Jeszcze będziesz na górze przez chwilę. Tak, nie jestem jeszcze z godziny na pewno. Ja mam takie dzień, że cały czas mam jakieś spotkania.
Przed świętami.
Się. Tak, mam raz do roku właśnie takie odbiory. No, strasznie długo trwało. No ale już.
No, czasem tak jest. Ja też przed świętami to wszystko tak się dzieje. Zawsze mamy było tak luźniej trochę w tym roku, jakoś więcej.
Ale jesteś, kiedy wracasz?
Jestem, do 11 stycznia jestem.
To już nie wtedy, bo tutaj znaczy w Warszawie jesteście?
Jestem z Radomia.
A, w Radomie. To jest Warszawa. Tak, proszę. Dobra, no dzięki.
Ja dziękuję Wam za zaproszenie, bardzo mi było miło.
Przede wszystkim, bo to wiesz, no to się zdarza...
mocno, więc to jest powiedzmy jeden z tematów, na który pracowałem. Tak?
No ale fajny, taki wyszedł właśnie pokaz, że naprawdę super, bardzo zrzutowywało.
To się cieszę bardzo.
Także dzięki.
Dziękuję jeszcze raz i do zobaczenia w takim razie.
Do zobaczenia. Wszystkiego dobrego. A właśnie, wszystkiego dobrego. Trzymaj się. Dzięki. Staram się wyłączyć tutaj, ale i tak jeszcze chyba muszą przejść. A, chusteczka może jeszcze. Widzę, że jeszcze jest. Też może.